Hi, so this stream will be a little bit different than the last couple of weeks. So I thought I would try a bit of an experiment tonight, and I'm going to try to implement a JIT compiler in one evening. And of course I can't do that completely from scratch. I'm going to use the RPython machinery for that. Right, and so the language that I'm going to implement that or make that JIT for is called lookups, and it's from this book here called craftinginterpreters.com. It's a really great book. I didn't read all of it, but I read many parts, and I like it quite a bit. Hi Panos, hello Matti, nice to see both of you again. Right, so this is the book, and it's a very nice introduction to implementing languages, and it basically roughly has two parts. It defines this, or three parts. It defines this nice language called lookups, which is very it's imperative and object-oriented and quite minimal. And then basically it talks about two different strategies of implementing this language. A tree walk interpreter and a bytecode virtual machine. And the bytecode virtual machine is pretty close to what, for example, CPython is doing. And the tree walk interpreter is much simpler. It parses the program into an AST, and then basically it has an AST visitor to interpret the program. And we're going tonight we're going to focus on this part, partly because I didn't find any nice Python-based implementations that are complete enough to be interesting for the second implementation strategy. So right, so what I did is basically I searched. I mean, people are following this book and are implementing all kinds of variants of this language in many different implementation languages, and there are some Python implementations around. And I looked at some of them, and I settled on this one by Ruel Adrians called JIT. It's here, it's very nice code, it has nice CI, it has tests, and it's written in idiomatic Python 3. So I had to go and throw all that out because RPython is Python 2 based. So I had to kill all the type annotations and all the f strings, and I broke all the tests and I didn't have time to fix them. Anyway, so I have a completely terrible version of this implementation, and all the problems that we see tonight are due to me and not due to Ruel, because his code is really lovely. Right. Okay, so let's start a little bit by looking at a few example programs. For example, there's a very simple one called loop, and there are two loops here. It defines a main function. It calls it down here, and then there's a while loop that increments a by 1 and prints a 10,000 times, and then there's the same loop basically as a for loop with only 1,000, but the same approach. So that's kind of basically what the language looks like. It has curly braces and yeah, vaguely C style. It's dynamically typed though. It only has one number type, which is a float. So all the numbers are floating point numbers, like say in JavaScript. But it also has a number of object-oriented features. For example, here you can define classes and have methods in the classes, and init is the constructor, and this is basically the instance that we're initializing or accessing. And here we have a node class, and we write some field, and that's it. And then we have a list class that has a get item, a pop, and a push. And the main function pushes 2,000 numbers, and then it uses get item to get each of them. And get item of a linked list is linear in the index. So this is a quadratic loop down here because it goes through the whole linked list and it gets all of them once. So that's it follows n times n minus 1 divided by 2 number of list chains, so that's quadratic. That's kind of bad, but anyway, I don't really care about this program too much, just to sort of give an impression of the kind of stuff you can write. Right, okay, and basically this is a method call, and this is an attribute read, and the usual stuff that you expect. Right, so how is it implemented? There's a parser, there's a tokenizer and a parser that I'm going to ignore, and then the parser will instantiate AST classes. The AST classes basically represent all the features that we've seen so far. There's an assignment, there's a class for assignments that says I'm assigning a name, setting that to a value. There's a binary operator with a left and a right operand and an operator. There is a call AST node that has a callee and the parent node, and then a list of arguments. There's a get, which is an attribute read, which has an object and reads a name. There's a grouping. It's not really complete. I mean, it's sort of a mixture between a syntax tree and an AST, because it contains some syntaxy things that aren't really necessary on an abstract level, like the grouping here. Right, there's a literal, which is a value, and so on. And those are the expressions, and then there's also a file with all the statements. There's a block which groups stuff in curly braces. There's a class definition, there's an expression statement, there's a function definition, there's an if statement, a print statement, a return statement, a variable declaration, you need to declare your variables, a while loop, and then a top-level program node. Right. So how do we interpret this? This is interpreted by using this interpreter class here, which is a visitor, follows the visitor pattern. It basically walks the AST and executes the stuff that it sees, and we can look at something like visit binary expression, and then here we have a switch on all the operator that it implements, and it does stuff like, okay, if we're implementing greater, then we're checking that both of the number are operands, left and right thing are operands, and then we're comparing them and making a new bool. And so for the other operators as well, there's a minus that subtracts stuff, a slash that divides, and a star that multiplies, and so on. So it's a pretty standard AST interpreter, which you might or might not be used to. But yeah, it's not completely magic. Yeah, there's a super keyword that I broke and didn't bother to fix because my example programs didn't use it. Right. Okay. So that's the interpreter, and let's look at the data form structures of the interpreter. There are a number of classes that represent objects that are handled by the language, and they're in here. Oops, I wanted a new tab actually. Right, they're in here. There's a root class, and there's a bool, and then two subclasses of that, and there's singletons. So there's a true and a false, and a new bool that takes a regular bool and turns it into a wrapped bool. There's a nil, which is like none. There's a number, which has a num field that stores the Python level float, and there's a string. And then there are a number of more complicated things like instances, classes, and functions, but we'll get to them later. Right? Yeah. So that's the basic data structures. And then we can actually go and run this stuff. For example, we can say, oops, is there something cut off at the bottom? Looks like it. Resize. Yeah, there's a reason why I had to switch. My graphical interface. I'm going to get to that later. Actually, so one of the helper programs that we use in RPython to visualize stuff actually consistently crashes GNOME, which I figured would be somewhat annoying during streaming, so I had to switch to XFCE for tonight. Yeah, Matti, that's a great question. Well, extremely well spotted. This W underscore convention is from PyPy. So, oh, hi, Rule. Nice to see you. Yeah, so the original code didn't use that, so I introduced it. And the reason for why I had to introduce it is that otherwise it doesn't fit into the typing discipline of RPython. So I went and introduced these classes yeah, otherwise the code previously was mixing floats and none and strings and all kinds of regular Python types in the same location in the interpreter, and that wouldn't be valid RPython, so I had to go and change that. Right. Okay, so what we can do now is we can actually run this stuff. Let's start with the loop. Right. It counts up to 10,000, then it counts up to 999, and that's it. There's also something simple like star hello, which is simple, right? It prints 3. There's a Fibonacci, prints a number of Fibonacci numbers and that kind of stuff, right? And then I wrote a really stupid benchmark program. Let's look at it first. Right. It's really just a stupid while loop that counts up to 1,000,000. And right, let's run that. Do I have enough patience? 20 seconds, amazing. Right, let's actually run it with PyPy, that should work too. PyPy is faster, right? Ooh, great, 20 times faster. But of course it's still not really fast. I mean, counting to 1,000,000 should basically be instant. So, and that's what we hope to address tonight. Right, okay. So much for the introduction to the interpreter. I mean, it's not complete magic. We're now going to basically dive right in and add a JIT to it. So the most expensive thing about this interpreter is that it touches all these AST nodes all the time, right? So in order to run, let's look at the other example program. In order to run this, it turns it into an AST and then it walks the AST all the time. For example, let's look at the while loop. So the visit while statement has a while loop inside, of course. It implements the while loop by using a while loop, and what it does is it says evaluate the condition, and as long as that is truthy, execute the body. And so it all the time for every iteration of the loop, it needs to evaluate this condition, which means it looks at the AST node of this condition, which is a binary comparison node, and then it looks at the left child, which is a variable lookup, and up, and the right child, which is a literal number. And so it walks these. It has method calls to walk this tree over and over and over again. And that's very inefficient because it needs to inspect the AST nodes again and again and again and again. So we want to get rid of that, and the way to get rid of that is to use RPython. And before we actually get to the JIT generating part of RPython, let's first talk about RPython without talking about the JIT. So RPython is a restricted subset of Python 2. That we mentioned on the stream a couple of times before. It's the language that PyPy is written in, and it's also the language that I converted this interpreter into. So what we should be able to say, I wrote a target here. The target is basically a kind of makefile. It has a main method, and then it has a target method that says I'm trying to compile the main function. And then the main function can use all kinds of other Python code, and it will compile all the code that's reachable from main. And RPython has to adhere to a number of restrictions, and the most important one is that you cannot mix types. You cannot in RPython code you cannot mix a float and a number. RPython is type inferenced, so it will infer all the types in your program, and there are a number of things that are forbidden. And one of the things that is forbidden is to use a float and a string in the same variable in your program. And the original program did that. The original program evaluate could return any Python type, like a string or a float or whatever. And that's forbidden in RPython because it's not obvious how to represent such a variable in C that can hold both a float and a string. So that's why I had to go and introduce all these classes, because now in the change interpreter, the evaluate function returns an instance of a subclass of this root class. And that's fine. I mean, basically the type is then inferred to be this base class or any subclass of that, and that's a valid thing to be stored in the same variable in RPython. Hi Tobias, nice to see you again. Right, so what we can do now that I changed the code to be RPython is we can take the interpreter and compile it to C. Let's actually do that, just so that we saw it once. Let's try. It's possible that we need a Python path. Right. Right, so what running this program does is it will type analyze the whole interpreter and sort of figure out the type for all the variables, and then it will lower all the abstractions, all the operations that are going in the program, and it will lower them to C, and then spit out C code, compile that, and then you get a binary. And while it does that, it draws a Mandelbrot fractal, because somebody thought that was fun once. Right, and it's basically a rather slow process, and it's not incremental, so you need to do it again and again, and we try to avoid having to do it, but it should, for the small interpreter, it should take 2 or 3 minutes. Right, so in this first phase, it infers the types. In the second phase, it lowers the operation to be more on the C level, and then there's a number of optimizations. And then it will build in a garbage collector, because RPython is garbage collected. So in the C binary, we need to garbage collect the memory somehow, and so it builds a garbage collector and sort of fuses that into the binary. Right. Actually, building the garbage collector probably takes as long as building the interpreter. But now we are done with the GC. Now it optimizes the GC, and then it spits out C code. Any moment now. Right. Now it spits out C code. Right. There are the C files. You can actually look at one of them. So let's look at yaplogs interpreter, and no, I shouldn't do that because it's small. Right, here's the C code. It's very scary and long, and you should never read it, but we can look at the C code for the while statement, for example. While statement. And it turned our cute, harmless method here, which is just 2 lines, into hundreds and hundreds of lines of C code. Oh no, it's just 2 pages, right? And there's a while loop here, and then there's tons of stuff going on. Okay. Anyway, don't read the code. It's not important. You almost never have to read it unless the C code generator has a bug. But nowadays it's very well debugged, so it very rarely happens. So I'm going to close it again. Right, so how far are we? We were done. We have a binary, and the binary behaves exactly like the Python code, hopefully, and we can run it to run bench loop, and it's much faster. it's of course even faster than running the interpreter with PyPy, because the interpreter is now in C, and C is fast, and all the types are inferred, and it has a nice garbage collector inline, so it runs the original 20 seconds in 0.3 seconds. We might have to increase the million counter to something larger later. Right. Okay, cool. So step 1 is done. We, instead of having a slow Python-based interpreter, we now have a fast C-based interpreter, but it's still an interpreter. It still has the AST. It walks the AST, and it fundamentally behaves the same. It's just written in a more efficient language. So the next step is really to write a JIT. So, and as I said, we're not really writing a JIT. We have a tool to generate JIT compilers, and that's part of this strange RPython thing here. And basically, you need to tell RPython that you want to build in a JIT, which you do with -o JIT. And when we do that, it will try, and then it will fail pretty soon, because the JIT generation isn't completely automatic. So the JIT generator only works for interpreters, and the generator cannot really magically find your interpreter in the Python code that you give it. You need to basically point out where the interpreter is to be found, and you do that by defining an object that's called a JIT driver. And so what we do now is we go to the top, and we import the RPython library that is responsible for defining JITs. And now we can say, okay, we want to have a JIT, so we need to define an instance of this JIT driver thing. And I never know how to capitalize it, but I think it's like this. Right. And the JIT driver takes a number of arguments, which we'll fill out later. So that's the one component that we need. The other component that we need is we're generating a specific kind of JIT that's called a tracing JIT. And a tracing JIT is really focusing all its effort on loops. It's trying to improve the performance of the loops in your program. And the reason why it focuses on loops is in order for a program to take a long time, there needs to be either recursion or a loop. Let's deal with recursion later. Actually, there is a way to do recursion with tracing too, but at first, loops are the things that is slow, so let's focus on loops. That's the main motivation of a tracing JIT. So we need to tell the JIT generator how it can identify the loops in the logs programs, right? So we need to tell the JIT generator, here is the place where the logs programs loop, where the interpreter executes the loops of the logs programs, and that is here, right? That is in this visitor method, where we have a loop when we interpret a while statement, and actually the for loops are turned into while AST nodes, so we don't really there isn't really a visit for here, right? It's really just here, and so we need to add an annotation here that says it's actually a method on the driver that says here is the place where loopiness happens, and that's something called a JIT merge point. Why it's called a merge point is a little bit technical, but the basic idea is that we call this method on the JIT driver called JIT merge point. And that's basically it, right? And the execution that we started before says error, no JIT merge point found, and now we added a merge point, and now we can start this again, and we will get a JIT, I think. No, we can't. Okay, so there are some arguments to the JIT driver constructor that are mandatory, so I need to talk about them. I thought you can have a driver without any arguments, but apparently that's not true. So this method is not completely enough. The other thing we need to tell the JIT generator is we need to classify all the local variables here into two classes. The one class is the variables that store the program. And the variables that store the program here is the statement. That's an AST node So that is the variable in the interpreter that stores the program that we are currently executing. So in an AST interpreter, that would be the AST that we're currently running. In a bytecode-based interpreter, it would be the current bytecode. Right, and so the two classes are things that store the program and everything else. And we give them colors, so the variables that store the programs are, we call them green, and the variables that store the rest, we call them red. So in the constructor, we need to tell it the names of the green arguments and the names of the red arguments. So here we can say, what's it called? Reds equal self. That's the only other local variable. And greens equal statement. Right. So now we have classified the local variables at the point where we call the JIT merge point method into these two classes. Right. There is no other local variable here, just self and statement. And so for technical reasons, we need to say this now. Self equals self, statement equals statement. Right. And now, when we run this again, let's wait for a couple of seconds to see whether it now finds a JIT merge point. Right. So that's basically the minimal set of annotations that you always need to have the JIT generation do anything at all. Right. So with these two things, a driver and the classification of variables and a call to JIT merge point, we will get a JIT. We might not get a good one, but we will get a JIT that will produce machine code from our logs programs at runtime and then run the machine code. And let's see, we're still not past the dangerous point. I won't let this run till completion now, because it takes like 10 minutes. But I want to see that, okay, the JIT compiler generation has started. That's a new phase that we didn't have before. And that takes a while, like 6, 7, 8 minutes. So it makes a JIT, and then it will compile the JIT. It has 110 JIT code instances. And then it will compile the JIT to C. And then afterwards, we get a binary that behaves like before, and just that it has a JIT. So we're done. I mean, the evening stream is closed. We can go home because this thing will now build a binary with a JIT. It will be a very, very bad JIT that doesn't produce particularly good code, right? But it will produce code. And we're now going to switch tracks a little bit, though. So the current development methodology that I'm using is really inefficient, right? We need to add this annotation here. Then we wait for 15 minutes. Then we get a C-based binary and we run it, and then we see whether we can stare at the assembler and we can see that whether it's faster or not. And probably in the beginning we need more annotations because those annotations we have so far are minimally enough but not really good enough. So we need to add more. Then we need to wait for another 15 minutes, and it's just not. I mean, it's not a very good way to work. So there's basically a really hacky shortcut to make our turnaround time faster. Right, and I'm going to show you that now. We can leave that running in the background. Actually, no, let's stop it. The output is not going to be useful yet. Let's switch to the other way of working. And the other way of working will not produce a C binary. It will run the JIT generator without producing a C binary, but sort of running it for a little bit and then running the JIT as Python code. And it will be quite slow, and it will not really produce machine code, but it's basically a way to debug the JIT by sort of having it emulate what it would do after translation to C. And it also has a number of visualizations to show what would be happening if we translated this to C. And I mean, one annoying thing is that it's actually a really hacky file, and every small interpreter that wants to add a JIT basically copies around this hacky file. It has weird imports, scary imports, but the interesting bit is down here. It's also run in a really strange way, as you're going to see in a minute. But it has basically test files down here, and the test files contain stuff like run string, and then there's some logs code here. And so if we run these tests, what will happen is it will emulate the JIT, and it will show us not really the machine code, but something close to the machine code that would have been generated for this logs program, right? And that is much quicker. It only takes 20 seconds, and in that way we have a much better turnaround time. We can look at the would-be generated machine code and see whether we like it, add some more annotations to the interpreter, run it again, see whether the code improves, run it again, and so on. So let's actually run it. So it's also run in a really weird way. It's actually run by saying, by feeding it to PyTest. And let's actually focus. So I prepared a number of sensible first programs. So this is the first program that really just a loop. I mean, we want this to be fast in any case. There's a slightly different version here. What the difference is, I'm going to tell you in a bit. There's a version here that calls a function per iteration to see whether we can inline this small function in the machine code. And then there's a more complicated version that creates instances and calls methods and so on. But let's focus on the really simple one here. Okay, so let's run it. So we say loop. Right. Okay, we need a Python path. Annoying. This maybe. Right. As I said, what this does is it pretends to build a JIT and then runs it without producing C code, and then that way we get output faster. Right. And then it doesn't actually produce machine code, but it produces stuff that is one layer of abstraction above the machine code. And we have this visualizer here, and actually that visualizer is what crashes my GNOME. That's why why I'm using XFCE today. And what you see here, I mean, it takes a little bit of time to get used to this view here, right? And I mean, you can zoom in and look at it more closely. Apparently you cannot zoom out completely, but that's okay. And these rectangles here are the basic blocks of the generated machine code. And a basic block is basically a block of machine code that is running in a straight line. So when you run the first line, it will continue running to the end. And at the end, there is a jump or something. And then we have here this arrow to the next block. And then we run this block. And then here we see that we have a loop. So we have a jump down here and then a jump back. And that's basically the while loop. That's basically a while loop. That's the machine blocks that correspond to the while loop in our source program here. So what this is something called, you know, I cannot zoom further in. This is the maximum zoomage. Plus does nothing. Only minus works. So I fear this is as big as it gets. Yeah, the viewer was really written in a time when screens didn't have as much resolution as they do now. So I mean, somebody needs to hack it. On my high DPI external monitor, it's completely unreadable. Matti, are you very unhappy, or do you want me to continue? I'm going to talk about this a little bit. Okay, so what you see here is basically something called IR. It's called intermediate representation, and that's basically a representation of the machine code that is sort of above the machine code level. So it's because this IR is shared by all kinds of different backends for different CPU architectures. So it's, I mean, you don't really need to understand all of this, but this is basically a representation of the machine code that the JIT will have produced in its current form. And so what we need to do now is we need to inspect this at least a little bit, and we need to sort of ponder, and I need to use my knowledge of the JIT compiler generator, and we need to add some more annotation to the interpreter in order to make this code better, right? And that is, yeah. I mean, in the beginning, it's really quite unapproachable. But maybe we can start at the top. The top in here is a variable. Is basically an input variable, and there's only one input variable. And the input variable that we have here is the interpreter. All the red variables appear. That's only the red variables are left as variables. The green variables completely disappear because we specialize the machine code on the green variables. So there is one piece of machine code per AST node that we've seen, right? So at runtime, if we see a new while loop that we run often enough, we will produce a piece of machine code for that while node, for that AST node only, and that means that the green variables disappear, the red variables are left, and so we can hover over a variable and see where it's used, right? And for example, here it's used to store it somewhere, and here it's used to pass it into a call, and down here it's passed somewhere further, right? And all the other variables that we get are numbered 0, 1, 2, 3, 4, and so on. The prefix, the letter prefix, is the type of the variable. So we have a reference, which is a pointer. The interpreter gets turned into a pointer, and then the I means it's an it's an integer, and somewhere down here we have f for floats, right? Okay, and what we see now, and that's the first thing that we have to address, there's a get field, and there are lots of get fields actually. There's a get field here and get field here and more and more. And the get field is basically an attribute read, an instance attribute read. And here at the end of the line, you can see what attribute it's reading. So it's doing a get field of a statement.block, which is a class in the AST, and it's reading the env size. And down here, there is a get field of a binary, the left, right? And the thing in the front here is where it's reading the left field of. And the thing that it's reading the left field of is a pointer. So what this says is, I have a constant AST node, and I'm reading the left pointer, the left operand of that. So we have a constant binary node, and we're reading the left operand. And that is bad, right? Because it means that we have a pointer dereference here, and we don't want that. And we don't need that either, because the AST nodes are immutable. The language doesn't really support us to mutate the AST at runtime, right? So the first thing we need to do is we need to add annotations into the AST classes to say all of these classes are immutable. We cannot change any of its fields, any of their fields. And if the JIT knows that, it can constant fold reads of these attributes from the constant pointer to instances of AST nodes. And that's quite common. I mean, one of the very common annotations is that we can go to the RPython class and say this field of the RPython class is immutable, and it will never be changeable at runtime, and then the JIT can use that information and produce better machine code. So, okay, that's our first step. And it's a bit of a boring step, but we'll do it. We'll basically go through the classes here and add this annotation, which is RPython specific. immutable fields, and it's a list. It's a bit like a slots declaration. Like this, and we kind of, to be on the safe side, we should do it a bit everywhere. Right. So here we have left and operator and right. And here, oops, we have, this is a little bit interesting. We have a callee and a parent, which is the parent token, which we probably don't need. And then we have the arguments, and the arguments are a list. And we want to say that the whole list is immutable, not just the pointer to the list. And there's this syntax for that. It says argument stores a list, and the whole list, none of the elements of the list can be mutated either. And if we do that, we should make a copy of the list for complicated reasons. But it prevents, I mean, one thing it does, it prevents sharing. So if somebody else has a reference to that list, they cannot mutate the field through that reference. Okay, let's go on. Opt and name. That's reading. I'm not using any groupings, I think, but let's do it anyway. Immutable fields, value. As I said, a little bit boring and a little bit manual. This and okay. This, I don't think we read this keyword field in the interpreter, but let's be on the safe side, do it anyway. Right. Okay, so those were the expressions, and then now we have a number of statements. This unimaginatively named envhaver node is also new in my version. I'll talk about the environment a bit later. So class statements, they probably don't matter, but let's do it anyway. I mean superclass. So if your program depends on making class creation really fast, then you probably should write a better program. Function. So name, and again params is a list, and we want to make the whole list immutable. Hi Julian, good to see you. Right. Okay, that's good, and we need to copy the params list. Function if, almost through, condition, then branch, else branch. So keyword value var name initializer condition body, and then there's a program. I don't think we need it here. Right, so that helped. We added lots of immutable fields, and now the AST is completely rigid, right? The AST, all of the fields of the AST are known to be immutable. So if we start from a while loop that we know is this specific while loop in our program, then recursively down the AST, everything is completely immutable and completely static, and that means that the JIT can optimize away all the accesses to all the fields of the AST nodes. So it can really generate code that corresponds to what the interpreter actually does for the concrete AST nodes without having to worry that the AST's nodes change, which cannot really happen in practice. So let's restart. And now the shape of the generated rectangles should be a bit different. And this is very much the style of working. You add some annotations, you run it again, and you see whether the annotations helped, right? So now the rectangles are a bit wider. That's good because it means that less operations are generated. And so now we need to sort of enter this process where we make them longer again by inlining more, and then by making them wider again by sort of making sure that more stuff gets optimized away. And the first problem that we see, there's a call in here. There's a call. It's a call that has a scary name. It's called call may force, and it takes something, and we don't quite know what. So we need to figure out what that call here is. And the first thing here is the function that we're calling. Unfortunately, this viewer doesn't resolve the function name, but we can also look in the terminal and see here's the same call may force. Oops, I didn't intend that. And it says execute block. So the thing that we're calling here that we're not inlining is called execute block. So the next thing we should make sure is that the JIT inlines into this execute block. So execute block. Right. Okay. We can understand how we get there. So the while loop contains the while loop's body is a block, and so we end up inlining the visit block statement, and then we see the execute block, and we do not inline the JIT does not inline this one. It leaves that as a call. And there's a very simple heuristic for the JIT to decide when to inline something and when not to inline something. And it inlines something if the method does not have a loop, right? So it will never inline loops. And the reason for that is that the tracer cannot inline loops. It can only unroll them. And that's potentially dangerous because it's not safe to just unroll any random loop that you happen to find somewhere in your program, right? Because the loop could potentially run 5 times or 500 times, so unrolling it isn't safe because you might generate code that doesn't really work particularly well because it unrolls 5 times, and the next time you run it needs to run 500 times, and then you need to generate more code, and that's kind of bad. So let's actually add an annotation here that this function can be inlined because it is safe to unroll this loop. And the reason why it's safe to unroll this loop is that the number of times that loops runs is completely dependent on the AST. So it gets statements. It gets the statements, for example, in the body of the while loop here. In this case, only one statement, for example. And it will go through the statements, but the number of statements in the block that never changes. It's always the same number of statements in that specific block. So it's safe to unroll this thing. Tobias asked whether the JIT is imported, and yes, it's imported. So that's the first thing we do. We tell the JIT to please inline this, because then you see more of the execution of the program. So let's try again. New annotation, rerun. Right, let's see what we get. Right, we do not have the call may force anymore. There's another call here. Let's see what the call is. Interpreter ancestor. I don't remember what that is. We might want to inline that. No, I do remember what that is. Okay, so we need to talk a little bit about how the environment is represented. I mean, the environment is basically the data structure that stores the values of all the variables. And it's lexically scoped, so that means you have a block here, you define with a var keyword that this is the block where the variable lives. Then you have a sub block here, and when you execute that, you need to refer to the variable in the outer block. And that means for every variable, we compute how far off the variable is. And that means we need to go up one environment, and then we use the first variable here because it only has one. And so there's an ancestor method here that basically walks up the nested environments and a fixed number of times, it's called the distance, and then returns the correct environment. And then we have a, where is it? Where do we call ancestor? Yeah, lookup variable. To look up a variable, we go out a number of environments, and then in the outer enclosing environment has a list, and we go to a fixed position, right? And going to given that it's lexically scoped and statically scoped, we pre-computed the distance and the position. That means it's safe to unroll this loop too, because the number of the distance is a constant, right? And we can see that here. So we have the call here, and it takes something, and it takes the distance, and the distance is the constant 1. So we want to go out one level. So we can inline that. Let's save and run again. Okay, the shape changes, that's good. And now, okay, that takes tons of experience, but now the code looks good. And you don't know that, but let's actually look at just the kind of operations that we've left. We have a get field, which is a pointer read. We have a get array item, another get field. We're reading the token type of a token. So that's another, here we have a constant token, and constant instance of token, and we're reading its token type. We should also make that immutable. Okay, fair enough. We have two guards. I'm going to tell you what a guard is in a moment. And then we have another get field, a get field here, a float addition. That's not unexpected. We know that we need to add 1 in the loop body, and then 2 more get fields, again on a token, and then a get field from a num. We will talk about that too. And then we have a float less than to check whether we need to run the loop another iteration, and then a guard true. And then we enter, then we go around the loop again. So the loop is structured in a little bit of a weird way. We always peel off one iteration of the loop, so that the actual loop body is down here. So, and the loop body does only very few things. But then there's something called the preamble, which is basically a copy of the loop body up here. And so we always first execute the copy of the loop body, then we enter the loop body, and then we stay down here and go back and forth between these two blocks. So what's in the preamble is not that important because it only gets executed once. But then the stuff down here is the thing that should be fast. And what we're doing down here is we have a get field, we have an instance of number, we read the num field. That gives us a float, then we add that float, we check that that float is smaller than something else, have a guard true, and then we have annoying stuff. I'll explain the annoying stuff in a moment, but the stuff down here we get. And that's very cool because it corresponds to what the logs program is doing. Let's look at the logs program. So what the logs program is doing is, in the loop, it adds 1, it compares against a constant, and then it checks that the result is true, and it goes around again. And that's what we see here. We add a float, we compare the float against something, then we check that the result is true, and then we go around again. And then with some caveats. I mean, there's this annoying stuff that I haven't talked about yet, and then there are a few get fields. Okay, but while we were reading the upper block, we saw a number of things that should be declared immutable. And the first one is the token. So let's open the token file. So here we can say immutable fields, token type, a lexeme, a literal, and line. Okay, that's hard. Now it's immutable. That should help a bit. And the other thing that we see is we have a constant number and we read its num field. So we can go to the objects and say that, okay, the numbers have a constant num field. And the strings, I don't have any example programs with strings. I also don't think you can actually do anything with strings except adding them. So it's not so important, but let's add it here for completeness sake. Right, okay, let's try again. Stuff is happening. Right, and the shape of the upper block got better. It got a little bit wider. That means that there are less operations, and the stuff down here didn't change. Right. Okay. I'll talk a little bit about that in a couple of minutes, but let's actually pause and sort of meditate on this a little bit. We're actually in a super cool position now. We managed to produce machine code. I mean, remember, what we see here is a representation of the machine code that would be generated if we compiled this stuff to C, right? So if in the current state, if we take the interpreter, compile it to C, build in the JIT, if we run the loop, we will turn this stuff into machine code and run it. And we can do that in the background, right? Does it work? Yes, maybe. This takes way too long, and I should nice it, I think, so that it doesn't interfere with my streaming. Right. So this, let's just keep that running. It takes 15 minutes, but then we can look at what we get then. Okay, and we can also look at the diff. So the one thing we did, I mean, we added a number of annotations to our interpreter to make a JIT compiler. We added lots of immutable declarations. Okay, a little bit boring. We need to basically, in Python by default everything's mutable, and we need to say that in practice I expect to never mutate these fields here. And then the JIT optimizer can use this information to constant fold information, like reading fields out of constant AST nodes. One thing we needed to add. Then we need to have a driver that classifies the variables into two classes, reds and greens. We needed to have a number of these unroll safes that basically say it is safe to inline and unroll this function with a loop. And then we needed a JIT merge point in the while loop that interprets loops on the logs language level. And with that stuff, we get a JIT. And we get a JIT that's not entirely bad. So let's make a branch JIT. Let's commit. And start generating a JIT. So add a JIT driver, JIT merge point, a few immutable declarations, and a few unroll safes. So that's the basic thing. That's done. This is happily churning away. As I said, it'll take a while. And now let's get the graph again and think about it some more. Right. Okay. Because we did a lot. In the current state, what the JIT does is it will remove the overhead of walking the AST completely. So in the original program, the interpreter would again and again inspect the AST nodes to figure out what to do next. And the interpreter in that form is extremely general, right? For example, the interpreter can deal fine with mutating AST nodes all the time, right? Of course, we can't mutate AST nodes, so we don't really need that feature. But yeah, the interpreter would do that perfectly. But we don't want to be able to do that. We want to have static ASTs, so we added these declarations. And now the JIT will completely remove all the overhead of inspecting the AST. And instead, it will make a piece of machine code that looks loopy like this here, with a preamble and a loop body, and it will still contain quite a few operations that are superfluous, and I'll tell you what they are, particularly down here. I'll tell you what they are in a bit. But it will not contain any code that inspects the AST. So that's really good, because it means that the main interpretation overhead to look at the AST, or if we had a bytecode interpreter, it would be to look at the bytecode, is completely gone already. So we are at another point where we can claim that we have a JIT and we can now go home or go to sleep or whatever. So mission accomplished. I need a banner or something. Okay, but then there's the stuff here that I'm not really talking about, that I haven't really been talking about, and so it's now while we wait for the binary to be produced, we can actually talk about it. Because, I mean, interpreting, like looking at the AST again and again, is not the only thing that is expensive about running dynamic languages. And the other thing that's really expensive about dynamic languages is making all the objects, right? Every time we do an addition, right? There's an add somewhere. Where's the add here? Binary plus. Every time we do an addition, we check that the two arguments are numbers. Fine. I can show you the code for that. So that's one cost. One cost is that we need to do type checking. It's dynamically typed after all. Then we read the number fields, we do the addition, and then there's another really expensive bit, which is that we need to create a new piece of memory. We create a new instance of WNumber here, which is that class here. But that means that we need to allocate a new box for every plus that we run. So if we run 1,000,000 pluses, we will, in our example program, we run 1,000,000 pluses. That means that we will allocate 1,000,000 pieces of memory. And admittedly, this instance is only 16 bytes big, so it's maybe, you could say, not so bad. The JIT will, the garbage collector will get rid of them quickly, but still, it's a problem. All the time, every time we have a plus, we're creating these instances, and then they soon die again. I mean, they die in the next iteration. But the constant churn of allocating and freeing and allocating and freeing and so on is really expensive compared to C, which of course would never think of doing that. And so a really important optimization that the JIT does is something called allocation removal, or virtuals, or in other compilers it's called allocation sinking, or partial escape analysis, or scalar replacement of aggregates. There are all kinds of names for it. In PyPy we call it allocation removal or virtuals. And the virtuals make sure that if we have if we create a number that has a sort of predictable lifetime, then we don't actually create the piece of memory. If we create a piece of memory and we see that we make it here, we use it for a little bit, and then we don't use it anymore, then we will completely optimize away the creation of that piece of memory. And we can actually see that by making our code slightly more complicated. Let's actually add 1 and subtract 1. And now the interpreter will do a lot more of these allocations, because the interpreter will allocate a box for this intermediate result, and for this intermediate result, and for this intermediate result. So every iteration of the loop, it will create 4 boxes. No, wait, 3 boxes, not 1. And so if we, I shouldn't Control-C this, I should Control-C this. If we look at the graph for that, we see that the JIT is already able to remove some of these boxes, but not all of them. And yeah, this removing of allocations is a really important optimization that is one of the real workhorses of RPython's JIT generator. Okay, so the code didn't change, right? But let's look in here. Do we see something here? Maybe not. Ah, no, wait, I'm changing the wrong thing. Nothing changed because nothing changed. I need to change the JIT.py file. +1 -1. Okay. Now I should see something. Right. I should also see the extra addition and subtraction, because our optimizer for floating point identities is not really good, and I'm not even sure it's safe to remove that +1 -1. Right. Okay. So we have a float add, a second float add with the same constant, and a float sub with another constant, but we very specifically do not have any allocations in this block. And if we look in the terminal at the unoptimized trace, it's even harder to read here, but it's basically, it's the same operations before the optimizer does its job. We see the float add, and then we have an operation called a new with vtable, and that's basically an instantiation of an instance, like an instantiation of a class. It instantiates a number and it stores into its num field, right? So in the unoptimized version, we make 1, 2, 3 boxes, like instances of that, and the optimizer is able to remove several of them. But the operations that we haven't talked about so far is the remaining one. The remaining one is that one here, and that one here creates a number. It stores the result of the add sub. It stores into that number, and then it will put that number into some array. And that array is actually the array of variables, right? As I said, the interpreter has an array. The interpreter is basically a variable environment, and it has a list of values, and basically when we have this assignment here, then it will be forced to store the box into a globally reachable place, which is the list of variables here, and then it escapes. It needs to be allocated, and so we see the allocation then, and the result of the allocation is stored into that array. We can see that it's that array because R1 comes from reading the field values out of R0, and R0 is our interpreter instance, right? So that's annoying because it means we still have one allocation per iteration, and that's pretty good, but it's not perfect. I mean, it's one step above what C would do. So we need to get rid of that allocation, and we get rid of that. Okay, by a very old but also sort of brittle technique, and it's basically it's a technique that comes from Smalltalk, and what the Smalltalk JITs do is in Smalltalk you also have a kind of a frame object, and the frame object is the object that stores all the local variables, and what the Smalltalk JITs did is that they special case those frames, and they say, I'm not going to bother filling in the frames. So the frame is basically an empty object, but it's only when somebody comes and uses introspection to look at the frame will it be automatically filled. And we have a mechanism for that, and it's called a virtualizable. That's a very fancy name. And that technique is sort of, it's quite a brittle technique. I'm not entirely sure that it'll work. But what we say with this annotation is that this instance here is special. And it's special in the sense that when you store something into the values field here, then you should not really store it into the field. I mean, just pretend to store it there and try to sort of get away with not putting anything there as long as possible. And that will allow us to remove the final allocation. Like this maybe. So yeah, the thing that we really need is this values star, which says that values is a list, and we really want to we want to not update this list. And then we need a really strange hint that I always forget how it works. It's JIT hint dot. Let me actually check. How does PyPy do it? JIT hint. No. Not here. So in PyPy there's also a frame object, and it has the same property. It's basically, it's where all the local variables and all the objects on the stack are stored, and there's a strange hint that you need in the constructor, and it's here. And I'm just going to copy that because I don't completely understand what it does. Whoops. I don't know what that was. Whoops. File system full. That's annoying. That means that it means that my recording is filling the file system. Okay, I did not really need that excitement. We were in the process of so for the YouTube people later, my hard drive was full at that moment, so I had to move the file somewhere else, and now I'm going back to the code. So there's this really strange hint that you always need in the init of something that you want to declare virtualizable, and I don't understand it, so I kind of cargo called it around. And you also need to declare your virtualizables in the JIT driver init. So to reiterate, what the virtualizable says is, I am a kind of frame. I store local variables or a stack or that kind of stuff. And please, JIT, try to keep all the content that's in this object in CPU registers or on the CPU stack. Don't update this object. Update it only lazily. Try to sort of update it as late as you kind of can get away with it. Right, and when we do that, then our problem goes away. Let's look at it. This is by far the most obscure feature of our JIT, I guess, and it's something that 0 people understand. So the people who wrote it kind of forgot how it works, and it's also a little bit brittle. It sometimes breaks. It might actually break for us later. Because it's really very closely tied to what yes, we get an amazingly unhelpful error message. That's the kind of stuff that I'm fearing. I'm going to basically try and continue with along these lines for, let's say, 5-6 more minutes, and if I'm not going anywhere, then we might kill it. Because the other thing that you get is if you do it like that, you can also only very carefully use this object now. And it says, okay, a virtualizable array, which is this values thing, is passed around. It should only be immediately used after read, and it's telling us where. It's done in lookup variable. Note that a possible cause is indexing with an index not known non-negative. Right, that's a very complicated sentence. But I think what it's trying to tell us, lookup variable in here, what it's trying to tell us is that we need to tell it that we are very sure that the position is always positive. And I think that might actually fix the problem. As I said, this is, I mean, if you're not following, we will get back to more understandable stuff in a couple of minutes. This is one of the most obscure features, but it's very useful if it works. So the same thing in assign. And the reason why you need that is that there's this nice Python feature that if you have a negative number, you index from the back, but the values field of the virtualizable is not really a regular list. It's this strange list that is updated only lazily. Yeah, we need to tell it that we're not using it as a Python list. We're doing only a very limited number of things, and indexing with a negative index is not something that's allowed. Another one in define, yes, of course. Here, boring. And the assert is basically a promise to the type inference to say I'm definitely not going to use. Yeah, thank you, Matti. There's a delay again, so Matti basically said that define is also a problem. Right. So now we're done. Now the code is super cool. Let's look at the loop body. Let's ignore the stuff up here. Now the loop body is great. We have an add, a sub, and a less than, a guard true. The guard true is a way to leave the loop. So we will run this only if we get a false here, and if we get a false here, we will leave the machine code, and then a jump that goes back to the beginning. So it really only, at this point, is really only floating point operations and that live in CPU registers. And so we get code that is, I mean, it's not really comparable to what a C compiler does, because a C compiler would recognize that the whole loop is completely useless, and PyPy never, I mean, the JIT can never do that, but it's sort of on the level of a non-optimizing C compiler. And that's really great. So none of all of the boxing overhead is gone. We don't allocate anything. We really just produce code that directly does all the floating point operations, and that's it. Cool, very, very cool. So I wasn't sure that would work. Right. We started that with a slightly broken version. So let's wait for that again. And now we will get, now we should get a binary that is really quite nice in a while. So we'll keep it running in the background. Right, okay, cool. Let's, I mean, that is really a very nice point to have reached. Basically, we reached the point where all the arithmetic operations get turned into something that's good, that's basically it's basically the base camp of generating JITs, right? Because arithmetic is really notoriously slow in dynamically typed languages. So the fact that we've gotten to a point where our arithmetic operations are sort of, they don't do any type checking, they don't do any memory operations, they don't allocate anything. We really just do the operations, and that's a very, very good point to have reached. By the way, there is still a little bit of type checking, because remember that this piece of machine code corresponds to, where's the file? To just the loop body. And the JIT will not look at the code just before the loop. Or you could imagine that we write this slightly differently. Start, and we call this with 0 here. And now if we look at this function, we don't know the type of start, right? We don't know, if we just look at the loop body, we do not know the type of XYZ going into the loop. And that means that we need a type check at the very beginning, before we enter the loop. and that is here. Here we have this guard non-null class, and that basically says, let me check the type of the current value of xyz. And then if we make sure that it's box, that it's number, and if it's not number, then we cannot use this piece of machine code. Then we need another piece of machine code that we might generate later. I mean, basically in locks that cannot happen because the only thing we can really add, I mean, we can add strings, I think, but we cannot compare them with less than. So the only type that makes sense here is a float. But in Python it's important. In Python you could execute this loop both with a float or an integer as an argument, and then you need two different kinds of machine code generated. So we need this kind of guard, this type guard, which is basically a type check before that checks one of the preconditions to make sure that we actually can execute the rest of the loop. Right. Okay, that's great. So very, very good intermediate position. And now there are a number of extensions. And yeah, I'm not sure I will get to all the extensions that I kind of had in mind for tonight. So one extension that's probably quite interesting is to look at globals. So I told you that we've been looking at the variable representation for functions for a couple of minutes now. But then in addition to the local variables, there's also the global variables here. The global variables are an instance of this globals class, and that's defined in the environment file. And here in the environment file, we see that the globals look like this. We have a globals object that holds a dictionary, and then we simply read and write that dictionary, right? And that means for local variables, we represent them efficiently by pre-computing their index into this values array at AST analysis time. But for global variables, we don't do that. And that's actually pretty similar to what Python does. Python also computes indices for the local variables, and the global variables are really represented by a dictionary. So we will actually get very different code if we write the same kind of loop, but we don't write it in a function, we write it on the global level, right? And if we do that, then we get a lot worse code. Let's look at that. What was it called? Loop global. So the next feature of the language that we or not the next, but one feature of the language that we should eventually think about is tuning globals. And yeah, let's look at the trace. Yeah, the trace, as you can already see, that the shape is worse, and it has all these calls here, and the calls are to a function called, we don't see the function names here, but if we look here, to a lookup, and that's basically a helper function that does the lookup in a dictionary. So it does hashing, and it probes the right places, and it's very complicated. And that means here, if we run the same loop on the global level, we have all kinds of gunk that manipulates the dictionary, and it will allocate stuff, and it will write into the dictionary and read out of the dictionary, and that's super inefficient. So one thing we should think about is how to make the globals dictionary faster. Actually fixing this program is actually hard. So let's actually skip that for a couple of more minutes. Let's look at something that looks harder, but it's actually easier, and that's that one here. And this one is the same loop in a function, but the increment happens in a helper function, and the increment, the x plus 1, happens in this inc function here. So what we can optimize next is this thing here, and that will actually force us to implement inlining on the logs level. Right now we only implement inlining on like all the helper function and the interpreter, but we can also inline on the logs level. And to do that, what's it called? Loop func call. Let's look at the trace for that. Right, and while we wait, we can also already go to call. There's a call expression, and we can already see that the first thing we will need here is an unroll save here, because this thing contains a loop here, and the loop is actually, we can unroll the loop because the number of arguments at a specific call site is always the same. So we might call it with one argument, and then we can unroll it once. Okay, we have the same problem again. That's very annoying. No, we don't. Okay, I'm confused. Okay, didn't know what was going on here. I feel we were full already, but it seems not. Okay, I know what happened, but it's not that the disk is full. That's which is good, right? So what I was saying is we can unroll this loop because the number of arguments for a specific call site is fixed. So let's add this, and something bad is happening here. We're not actually generating any. I don't know why. Call accept, right? Okay. Let's try again. It was something around calls, so maybe this thing already fixed it. Right. Okay, now we get a loop. And the loop is probably not great. And the loop is not great for a number of reasons. Right. One reason is that we haven't actually done anything about functions yet. So let's actually open the the function definition. The first thing we should do is we should make it immutable. So it has a closure and a declaration and an isInitializer flag, which says whether it's the init method of something, and there's a call, and the call has a loop again, so we can say unroll save, and here we didn't import the JIT yet, so let's do that, and let's try again. Right, I mean, so far we just did stuff that we understand already, or at least we've seen it already. I mean, we made some fields immutable. We added an unroll save saying that the number of loop iterations here is bounded, so it's safe to unroll it, and that's that. So let's zoom in, and right, it still doesn't look great, and so let's stare at it a little bit. Right, all kinds of things. Yes. I have a plan. So here we are reading stuff out. I mean, the first thing we do is we do a lookup of the function name, right? So the first thing, let's look at the code again. The first thing we do here is we look up the name inc. And inc, as we discussed, is a global name. So we will look in the global dictionary. So first we see a call here. And that call here will read something out of the global dictionary. So the get interior field is an operation that reads something out of a hash map. And then that is of type yaplogs function. That's to be expected. So we retrieved a function from the global's dictionary, and we're now going to call that function, right? But to be able to call that function, it would be nice to know what the function is, right? And right now we don't. Right now we read something out of the globals, and something might have changed the inc definition in the meantime, right? We don't know that. But we would really like to pretend that we know which function we're calling, because that would make everything easier. And we can achieve that. We can say to the JIT, please assume that the function that you're trying to call here is always the same function, right? So here in the call, we could say, okay, we check that it's a callable, but then after we check that it's a callable, we can say, dear JIT, please assume from now on that the function that you're calling is a constant, right? Because in practice, at any call site, we expect the number of functions that we see there to be small. I mean, most of the time we're always calling the same function. It's possible that in some weird situations, we might call a method and there could be a couple of different implementations of a method, but even then most of the time we expect there to be one implementation or 2 or 3 implementations. So there is a hint to the JIT that says the number of functions that we see at this specific call site is expected to be small, and that's called promote. And what promote does is it tries to make the argument constant. It tries to turn that into a constant, and then the rest of the machine code will pretend that the function is constant. And if we see a different constant later, we might have to produce different machine code. I mean, that's kind of the superpower of JITs. The superpower of JITs is that that it can always, produce more machine code. So if the JIT got itself into a crappy situation where the code that exists so far is no longer valid, we can do 2 things. We can stop running the machine code. We can instead go back to the interpreter, or we can make more machine code. And that's the feature that the JIT fundamentally has an advantage over a regular compiler, because the regular compiler, if the code that it produces isn't enough, then we have a problem. But for the JIT, we can always make new code if we are in a situation where we need new code, right? So in the chat, Matti is asking whether that will turn into a guard. Yes, that's right. It will produce a guard that I'm going to show you soon. And Tobias says that it was a good explanation. Thanks, Tobias. But you already know what promote was, so maybe you don't count. Right. So it turned into a guard. And as I already said, a guard is a kind of precondition that says the rest of the code only makes sense if a specific condition is right. And here we have the condition, I really want the inc function to be this concrete inc function that we've seen earlier, right? So I want the inc function to be this inc function here, and not some other inc function that somebody overrode the global later. Because in practice it happens very rarely, right? I mean, most of the time nobody is going to say later here fun inc some other inc function, right? And then we call main again. I mean, that's very unlikely code, right? In practice, most code doesn't do that. So it's a safe assumption to say that at a point where we call a function, we can assume that we always see the same function, right? And so now some stuff disappeared. There's still a get field of the params, field here, right? So that's an AST node, and we're reading its params field. That's an error that I made earlier, params. Right, it's a typo. Nobody stopped me. I was doing this boring and annoying thing, and of course I typoed something. So this field doesn't exist. It's not param, it's params. And I should fix that, right? And then one of the field reads should disappear, right? La-di-da. Okay, it's getting wider. Okay, so we still have the dict lookup, which goes to here. We have the guard value, which corresponds to the promote. And then the rest is good, I think. Yes. Okay, so that's actually kind of good code. We have the dict lookup in the global dict. And then we have a guard value that checks that we still have the same function. And then we immediately have the code that we had before. We have a float addition, a float less than, and then we go into the loop. And the loop looks similar to before, except that we do the annoying dict lookup in every iteration, because the JIT isn't very good at reasoning about dictionaries. It doesn't understand that within this loop, nobody can actually change the value of this inc entry in the dictionary. So it will redo the dict lookup again and again, which is a bit annoying. So, but then the rest is good. So we completely inlined the inc function because it's kind of nice and small. And then the fact that the addition here happens within the inc function, within that function here, completely goes away, right? So the only expensive thing here is that the fact that we need this dictionary lookup here to find the function that we want to call, right? So the dictionary lookup in the globals dictionary is the remaining problem for inlining. Yes, Matti, you're absolutely right. Without this viewer, we would be even more annoyed. I mean, as you already noticed, this whole JIT generation process doesn't really have particularly good UX, or I suppose it's not really user experience, it's programmer experience. So the tools are a bit rickety, but this one is definitely one of the things that kind of saves it from being completely impossible. And particularly for small interpreters. For PyPy, we don't really use it that much because it takes quite a long time to bring up the interpreter to a point where we can use the viewer. Okay, so I'm going to commit now. Should have committed earlier. Yes, so the other approach is indeed to read the textual logs that you see on the terminal here. You can also have them written to a file, and we have some syntax highlighting for them. Yeah, good point, Matti. Yeah, Tobias says he likes to read the log, but I think claiming that it's easier to read the log is a bit much. It's possible, but probably not that much fun. I mean, but remember, the alternative is having to emit binary machine instruction yourself. So this is, I still claim that even though the tools are kind of crappy, this is still much more enjoyable than having to deal with segfaults all the time. Okay, where were we? We were in a good place. So this almost is great. And the reason why it's not great is because we still have a globals lookup here. And we want to get rid of that. And we get rid of it by doing something much more radical to the interpreter than what we did so far. I mean, so far, we changed our interpreter by adding a few annotations here and there, right? And that's, we didn't really change the structure of the interpreter that much, but now we reach a point where that is no longer enough. We now really need to fundamentally rewrite this class, at least a little bit, in a way that makes it much easier for the JIT to deal with. And to do that, we need to sort of use our head and use our knowledge of the language to sort of make statements about the typical ways this language is used, right? The JIT at the moment will assume that the globals dictionary changes all the time, but that's not really true. The globals dictionary will actually change very rarely. I mean, stuff like this entry in the globals dictionary will probably never change, nor this one, right? So what we want to do is we want to make it expensive for the globals dictionary to change. We want to specialize on the state of the globals dictionary. We want to tell the JIT, feel free to assume that the globals dictionary is constant. and then you can constant fold all the reads from the globals dictionary. It's not completely true, because on the other hand, there are programs like this where the globals dictionary changes in every iteration. So we need to strike a balance between the two. So there are some kinds of globals entries that never change and some that change a lot. And we need to sort of deal with both of them. And this is actually a very common pattern. The first thing we do is we version the dictionary. We say we introduce a version, and the version is really just a tag. We could use a number too, but let's actually use an instance of a class, Python 2, so we inherit from object. And then basically we say every time we change the globals dictionary, we need to change the version. Right? And then if we do that, now that we have a version, we can optimize the read. We can say the read will always return the previous result under the same name unless the version changed. So we can say here, let's first read the version. And then we can say we promote the version, which says speculate on the fact that the version is probably still the same as earlier. And then we can say, okay, now we need to hide the actual dict read in a helper method. And the helper method gets the name and the version. And what the annotation says, it's an elidable function. Elidable is a really strange concept. And what elidable says, it's basically, you could also call it, it's a pure function. Right? It's a function that, given the same arguments, will produce the same result. Without the version, it's not true, right? So this function is not pure because, this function is not pure because if the globals dictionary changes, you could get a different result for the same name. But this function here is pure because in order to get a different result, we need to get a different version passed in. So if the version is constant and the name is constant, we will always get the same result. So now we can call that, we can say return self.get name and version, right? And this versioning is a very common pattern. If we have something that we expect to change slowly, we will introduce a version, we update the version every time it changes, and then when we read stuff, we can check whether the version is still the same, and if it is, then we can reuse the previous result. Okay, Julian is saying something. Yes, you could, but then I'm going for something more general. So Tobias says we should analyze the global dict to see whether it only contains functions and then assume that functions are really never changed. But that is much more limited to what I have in mind now. So it would be a good first approximation. Yes. So Tobias says, can we use an increasing integer here? Yes, we can. I mean, we could also just say version plus equal 1, right? That would also work. Of course, then we would have to deal with overflows, which is not likely on 64-bit, but yes, I mean, if you want for our small language, this should be fine, right? We're not going to overflow 64 bits of integer here. Okay, let's try that. So this is only half the solution, because right now we really assume that it changes very slowly, and we will completely change, we will throw away a lot of code when it actually changes. Every time we change the globals, any entry of the globals dictionary, we throw out all the code that uses a globals anywhere, and that's a bit too often, and we're going to deal with that soon, right? So now we don't get a call anymore. What we get instead is we read the version, we check that the version is 3, and then we don't read the function we don't have a hash map lookup anymore. because we know that if the version is 3, then inc is the function over there. And only if the version increases to 4 do we need to do anything else. Right? And now we have good code again. We don't have a dict lookup in the loop down here at all. And that means, yeah, that means we're happy. It means that this loop here is exactly as fast as this loop here. I mean, or as this loop here to be precise, right? So using this nice helper function here isn't costing us any performance, which is great because we want it to be cheap to introduce nice, I mean, we want to structure our code nicely, and yeah. The reason why I'm getting this error message, by the way, isn't because my disk is full, it's because I deleted Vim's temp file. So when I was cleaning out my temp directory, which wasn't very nice of me. Right. Okay, but let me actually be paranoid and check whether my disk is going to be full again. Maybe in 10 minutes. Okay, cool. Where are we? We solved this problem, but now we have a real problem with this code here, because what happens with the version here? Every time we run a loop iteration here, we change the global XYZ, and that means every time we run it, we produce a new version, and that means we cannot reuse the old machine code. That means we're back in the interpreter. We never produce a machine code, or probably worse, we produce machine code that we then cannot reuse. We run it once, throw it out, make some new one, run it once, throw it out, and so we're probably even a lot slower than the interpreter. That's bad. So we need to basically find an intermediate stage. We need to find a stage where we version those fields that don't change, and don't version the fields that do change. And for that, we have a simple heuristic. I mean, we use a heuristic, and we use what you always use, which is a level of indirection, right? We use a cell value, and so the idea of that is if we add a new name to the globals, then we version it. And if we mutate a name, then we update the version and introduce a cell, which is a level of indirection. And then the next time we change that global, we will change the cell, but the dictionary will remain the same. And so we need to, on assignment, we need to write a little bit more code. We need to say if this is annoying. Can I close the buffer and open it again? Probably. Yes, okay. So in assignment, we say if name in self.globals. If it's already there, if the name exists, that means we're overriding an existing name. That means we want to introduce a cell. Oh wait, okay, slowly. First, we're reading the old value, old val. Name JIT.promote version. Okay, we're reading the old value. If the old value is none, right? Then we know that we define it the first time. That means we do the old code. We write it into the dictionary, and we increase the version. If it's not none, we have two cases. If it's an instance of a cell, then we can update the cell, and we don't need to update the version because the dictionary doesn't change, only the cell changes. Otherwise, it's not a cell yet. That means we are overriding a value that we already saw. That means we need to say old val. We need to say now we introduce a cell. No, wait. Name equals cell value, and we need to increment the version for the last time for that field, right? So that's writing. And now reading becomes a little bit more difficult, because reading could return a cell, right? And if it's an instance of cell, we return val.value, else return value, right? And this basically, this is the approach. It's a little bit complicated. The idea is that it uses a simple heuristic. If you override a name once, then we assume that it's a value that changes often, and will produce introduce this level of indirection. But it means that if we introduce it further more and more, we won't increase the version every time, only the first and the second time. Tobias says that Theo says we shouldn't call them cells, it's just a GC handle. Yes, maybe. I mean, cell is an extremely generic term for this concept. So, Theo is Theo Tont, by the way, who is a now retired professor from Amsterdam. Oops. You should stop me if I make typos. Here. And I should have tests. Yes, if you always have a cell, then you lose the. Matti says, can't you always use a cell? That would always using a cell would already be an improvement. It would be an improvement because you don't have a hash map lookup anymore. But it would still mean that you need to promote the function here, and you can't assume. I mean, you know less about this function that is really never overridden. So we have this I mean, always having cell would be fine, but having this two-stage thing where you very eagerly introduce a cell but not immediately is already great. Ah yes, cannot unify instances with no common base class. Great, we're seeing all the problems in this stream. Here we see an RPython problem. A cell should inherit from I mean, a cell is kind of like an object, so it needs to inherit from wroot, from the base class of the object hierarchy. I mean, the cell type will never escape this file. Like, the interpreter will never see it, but we still need to give it a common base class to make RPython happy. Stuff is happening. So which function am I running? I'm running the func call one, and ideally that never changed, because in this one, yes, it looks good. It never changed because in this function we don't introduce a cell because the inc name is never overwritten. So let's now run the global thing, which is this one. And here we will introduce a cell for XYZ, and we will write into that cell again and again. Right. And it looks kind of good. There's no, what's that? There's a call. I don't want a call. Why is there a call? The call is, we allocate an array of size 0. I'm not really, it's not obvious to me why. Yeah. Okay, that's not fantastic. There's a strange allocation that I don't understand. But apart from that, we do not have a hash map lookup. The loop is good. The only thing that is kind of bad here is that at the end, we allocate a number and write that into the cell. Right? We have a cell, we need to store the value of XYZ into the cell for XYZ in every iteration. So in that way, the loop on the global level is slightly worse than the loop in a function because, because we still need to update the cell every iteration. Actually, PyPy is the same. In PyPy, loops on the global level are slightly worse than loops in a function. So please always put your benchmark loop into a function. Right. Okay. I think that's all I want to do for the global stuff. Right. There's this call here that I don't get, but I'm going to. I fear it's probably annoying, so I'll leave that for now. And right. Okay. Let's stop this. Look at the diff. Let's commit that. Add a versioning scheme for globals with cells for commonly changing values. Okay, it's kind of okay. Okay, small mental break. Let's look at the state of my hard drive. Okay, we're still doing kind of okay. And what we can do now is we can actually look at the binary that we produced a couple of minutes ago. It only takes 12 minutes. And we have a binary here. And that binary has a JIT. Unfortunately, we didn't save the non-JIT version, right? But we can run our bench loop thing, and it's even faster. If you remember, it was 0.1 second, and now it's 0.01 seconds, roughly. I mean, so let's actually make sure that we actually produce machine code, and there's an environment variable that allows us to tell the JIT to produce some debugging output. And what it will tell us is, okay, it produced one piece of machine code. It took 0.0015 seconds to produce this bit of machine code. And then there's some statistics about the operations. And yeah, and that's kind of what we expect. The bench loop has one loop. So we want one piece of machine code for the loop. And that's great. And if we want to, we can dig down into it. We can say, show us the optimized machine code, and then we will get the ASCII output that we already saw a couple of times, and it's annoying to read, but basically the loop is this thing down here. We have an addition, a comparison against a million, and then a jump, and that's it. And so it's the same kind of great machine code that we saw in the emulated version. So it's cool. So the binary that we produced a couple of minutes ago was already producing good machine code for the small benchmark that we have. Right. Okay. What is left? I mean, we're in a decent stage, right? We got quite an the first thing we did is we optimized locals and integer additions or arithmetic operations, which is important for dynamic languages because that's quite slow for dynamic languages often. Then we added some stuff to also deal better with globals by rewriting the way that the globals dictionary is structured. And then we also made sure that inlining of small function works and produces really removes the overhead of the function call of that small function completely. Also great. And basically what we did so far in the stream really shows the flavor of working on these generated JITs, right? You start with a simple language feature, and then you make the program slightly more complicated, add another language feature, and then you make sure that the code for that is great. And then you need to rewrite the interpreter a little bit to make it more friendly for the JIT. And then you try again with a slightly more complicated language feature. And good night, Matti. And so on and so on. And then you do that forever, right? Because there are always language features that you haven't touched yet. And there are always programs that you find that are still slow. But the basic approach is really that you investigate a language feature that you haven't looked at before. You look at the code. You tweak stuff a bit to make the produced machine code better. Then you do it again until you're happy. And if you're happy, you take the next language feature. As I said, basically forever. And yeah, the language features that we looked at. I'm repeating myself for the third time, I think, is locals, globals, and function calls. And then, of course, the next thing we would have to really get into is objects. And I'm going to very briefly do some of that, right? So I think that a sensible next target would be this micro benchmark. And what it does is it has a while loop again, and in the while loop it creates an instance of this class here, which sets in the constructor the argument +1, and then we call the getF function here. I'm not sure why it's called getF. I just typed something, and which returns the value field. And that tests all kinds of things. It tests how expensive is calling a constructor, how expensive is calling a method, how expensive is writing and reading a field, how expensive is allocating an instance, and so on. And yeah, so let's start a little bit. I'm not sure how far we'll get. I should probably sleep in 20 minutes, half an hour. But let's get started a little bit. Okay, let's first start at what classes look like. We haven't opened this file at all yet, so let's look at the classes. So the first thing we should do is we should add a immutable fields declaration. So they have a name, they have a superclass, and they have methods dictionary. Right, that's the first thing. And let's also open instances here. And instances, okay, what do they have? They have let's say you cannot change the class in logs. In Python you can change the class of an instance, but let's say in this simpler language you cannot do it. So let's say the class is an immutable fields, but then you have the fields dictionary, and that is mutable, right? It's a dict that stores all the instance fields, and you can change that, which is a problem. We're going to have to think about that in a couple of minutes. Right, and then let's make one further assumption. We have this find method here, and that find method takes a name and returns a method out of the class. Let's actually make a simplifying assumption. And the simplifying assumption is that in logs, let's assume you cannot mutate classes, right? Once you declare the class, then you cannot change the methods. So I wanna say, let's make our life a little bit easier and say, I assume that after you declared the class, you cannot add or change an existing method. That's not true in Python. In Python, you really have to deal with the fact that classes can change, and you deal with that by doing the same kind of versioning trick that we've already seen. But in logs, let's make our life easier for tonight and say you cannot do it once the class is declared. It's immutable. So Tobias asks is what the difference is between an immutable field and an immutable field square bracket star square bracket. And so the square bracket thing means that the field is a list and the content of the list is also not mutable. And we cannot use that here because we have a method, and that's not really a list, it's a dictionary. So we cannot use the star notation. That really only works for lists. Okay, so this already helps because it means that when we call a method, then getting the method object out of the method dictionary or potentially walking the superclass chain gets optimized away, because we say, okay, since we cannot change the classes, we can remove the looking up of the dictionary. So okay, let's actually look at the trace now. So the function is called create instance. Whoops. Okay, there's a missing import. It here. Oops. It's here, I think. Tobias says the fields here. Yes, but that's not really helping us. The fact that, yeah, I mean, I'm not even sure that this is so important, but instances are rarely constant. I mean, yeah, let's see whether we ever see, yeah, let's look at the trace, I think. I think you're right. You're right that after we only store to the fields instance variable once, and we will never mutate it. But I don't think it helps us to declare that. By the way, the strange spaces that we have here are from the fact that I used a script to rip out the variable annotations that the original code contained. Right, something breaks. Oops. Crash in JIT. That's scary. What? Ooh. Yay, that's not good. Something really bad is happening. So we're debugging the JIT. We have a Python debugger deep in the innards of the RPython JIT. And it's something around virtualizables. I already told you that it's one of the most brittle aspects of the code that we're using, and it's come back to bite us. That's very annoying. So what I will do now, in order to continue to talk a little bit more about instances, is I will just rip out the virtualizables again very quickly, because I don't understand them, and there's probably something that we're missing that we can change to make it work, but I really don't want to deal with them. So I'll do that, and we can talk some more about have some more fun with the instances and ignore that dark corner of RPython. Right, go away. Back to the basement. It breaks again. Promote a virtual. It's not good. I don't get why. We get a bad loop. Abort bad loop. We're doing something bad. Why? What did we change? Just this, right? Ah, no, we didn't really change. Which hint, Tobias? We didn't really change anything. We were only running a test that we've never run before. So it's entirely possible that this problem was always there. It's not really our change that added it. Okay, that's sad, because it means that we don't get a loop, and we can do one of two things. We can either, let's actually do that. Right, okay, let's stop it. Okay, this is getting increasingly obscure. I'm going to copy that into a new thingy here. Right, get a little bit of syntax highlighting. Anyway, if I can't find that very quickly, I'm going to stop, because that's just bizarre. Okay. So it's the promote. Remember that a promote turns into a guard value, and it's the promote of the function. So we make a new function, and then we promote that. And I think I know what the problem is. We haven't talked about methods. How do methods work? Right. We call bind here. What does bind do? Bind is something on functions. Yeah, right. Okay. It's too bad. Okay, so one of the promotes that we added before was wrong. And the reason for that is I thought that functions are safe to promote. That means that we don't see too many different functions, but it's not really true for methods. For methods, it's using the same bound method approach that Python uses. So every time you call getF here, it will make a new function object. And that means if you try to promote it, it's unsafe, because the next iteration you will get another one. So the JIT code will not be valid anymore. So we can either have a new class called method, the applux method. That would be one thing. Or we can actually go and remove the promote for function here. And we can do something slightly simpler, which is we can promote the AST that the function stores. So here, no, where's the applux function? Here. Because declaration, that's the AST, and it's safe to promote that. So we can say here, promote self.declaration. Okay, here too, and I suspect here too. Okay, that's safer. So the problem with bound methods, I really hope that, I mean, we're now known, I mean, what we should really do is we should have written proper tests that check that the shape of the machine code is as we want it to be for the simpler examples, in order to not break them now that we go to the more complicated ones. We were bad citizens, and for timing reasons we didn't do that, so now we need to sort of hope that we didn't break stuff. Okay, what's going on here? It's not so bad, right? I mean, given that we're doing really complicated things, the trace isn't really completely gigantic, but it still contains a bit of stuff, right? And let's actually start at the top. It has a find method call, right? And the reason why it cannot remove the find method call, remember that the find method thing is elidable, is that we do not know the class, right? We don't know the class, so what we need is, we need to say that whenever you actually read a method out of this thing, which is here, we want to promote the class, because we expect the class of an instance to change rarely. Let's try again. Should become a little bit better. That's fair. I mean, this is the standard thing to do. I mean, it doesn't look like it, but in basically in completely regular JITs, this would be called a polymorphic inline cache. And what it does is that if you have a method call side, you expect the number of different methods that you see here to be 1. I mean, in 95 or in 90% of the cases, for almost all call sites, we really expect to get always the same function, and so we use a polymorphic inline cache to optimize that case. Tobias tells me to check my hard drive. And it's indeed very low. So, but yeah. I think I can probably squeeze in looking at the trace, because the trace looked small. I mean, damn it. I let you interrupt my flow of thought. I'm too easily distractible or something. So let's look. This looks great. So there's some gunk up here, but the actual loop has an addition, a less than, and then we have an allocation. So what's up with the allocation? It stores something into some array. What array is that? I don't know. Ah, no, yes. Okay, the reason why we get the allocation is because we removed the virtualizables. Okay, too bad. Too bad for us. Okay. Okay, but it's still a really cool position. I mean, an old problem popped up because I gave up fighting against virtualizables, but we're doing super good on instances. Surprisingly good. So the allocation of this instance gets completely removed. And the method call, like it inlines the init, it inlines writing into the dictionary, it inlines the getF function, it inlines reading the dictionary. It's all completely gone, and we get a loop that adds, that compares, and then we have an allocation of the num. Okay, that's bad. But the fact that we don't at all see the fact that that we're using this class here, and all we had to do is we had to promote the class in order to do type feedback and have something like a polymorphic inline cache, and we had to declare that local that classes cannot change after creating them. Right. Okay. Let's take a small break. I need some water. In a kind of cool point, we started our first test that that was allocating an instance and calling methods, and basically a lot of that is great. But the reason why it works is because the JIT sees the allocation of the instance, and it can remove the allocation of the dictionary. It can understand the complete structure of the dictionary completely. And that is not always the case. And if we have a slightly more intricate version like this, then it doesn't work. And so what the difference here is that we make an instance before the loop, and so the JIT doesn't see the creation. Remember that the JIT really only looks at the loop. And then in the loop, we read we call the getF method, which reads a field, which we initialize to 1, but the JIT doesn't know that, and then we add x, y, z, right? And let's try that, and let's look at the trace of that. What's it called? Access. Yeah. Oops. I'm quickly committing. Right. Okay. So what do we get? We get the expensive thing. In the loop, I mean, we inline the method. That's already great, right? We have a method call here, which is completely inlined, which is fantastic. But the thing that we get here is 2 calls. I don't understand both of them, but in particular, we get a interior field, which is always the sign of a dictionary lookup. So in the loop, we need to do a lookup in the instance dictionary to read the increment field within this method time and time again. So we do hashing, we do probing, we look into the dictionary, and that's very annoying and expensive. So we should not do that. We should really speed that up. And for that, we also use a standard technique, and I'm not quite sure whether I can implement it quickly enough. That standard technique is called hidden classes in V8, like Google's JavaScript VM, or it's called maps in Self, which is the research language where this concept originated. And maps are basically, the idea of maps is that we have a lot of dynamism here in this implementation of instances that we don't really need in practice. The dynamism that we have is the fact that any instance can have all kinds of fields, right? We can stuff random fields into this dictionary, and the dictionaries of the instances of the same class can have completely different fields, which is not realistic, right? In practice, that's never the case. In practice, the instances of the same class will look basically comparable. So we want to specialize on the instance shape. We want to specialize on the names of the fields of that instance, because we expect that all the instances of this class here all have the same instance names. Not really the instance attribute names, not really the instance attribute values, but the names are always the same. So in order to do that, we need to split the names out of the instance and into their own object. And then in the instance, we only store the values of the variable fields, but not really the names of the fields. The fields go into a shared object that all the instances share that have the same kind of layout. And that object is called a hidden class. So the instance will have to change. The instance will look differently. It will look like this. It will have a hidden class. And it will have a hidden class at initialization time that says, I am empty. I don't have any instance variables. And it will have a storage. And the storage will also be empty. Right? And the cool thing is that the storage is now a list. And lists are much easier to access. Lists really just have an instance and you read out of them, whereas dictionaries are complicated. Okay, so now we need to define this hidden class, and we need to let's highlight that. We need to stop using the no longer existing fields dictionary. So what does a hidden class look like? A hidden class is basically an object that describes, as I said, that describes the layout. And it has two things. It has the layout, and the layout basically is a map from instance attribute names to positions in storage, right? And so we add an indirection. We move the dictionary to its own object, the hidden class. But the trick is that all the objects that have the same layout share the same instance of hidden class. That's one thing it needs. And the other thing it needs is a next dict, and I'm going to explain what the next dict does. And so now it no, it doesn't. Thanks for the rule says should it inherit from wroot? It doesn't have to, because it's not really a value that the user can store in a local variable. So the wroot is really just stuff that can go in a local variable, and that was the case for the globals because they're mixed within this dictionary. But the hidden class, we're never going to mix it into a place where a normal object goes. So we don't need to. But it's a great question. Yes. Right. So what we have now is lookup position, which takes a name and it returns it asks the layout, do I know this name? And if yes, give me its position. And now the get changes. It looks like this in class. Lookup position name.lexeme, and then we say if pos greater or equals 0, return self.storage at the position. Right. So that's that part. If our structure, if our shared structure says we know that position, we can go to our own storage and read at that position. So now we need to fix set, and set is complicated, right? Set has a simple case and a hard case. So the simple case is we look up the position, and the position exists, right? And then we can say self.storage pos equal value return. That's it. But now we have the interesting case, because right now the hidden class says empty, and our storage is empty, so we cannot ever reach that path, right? Because storage is empty. So we need to now we're in the case where we need to increase the storage. So we're adding a new name, so we need to increase the storage. That means we need to say, come on. Okay, what was the trick? If I delete the buffer and open it again, it will make a new temp file and keep working, I hope. Right. So now we need to increase the storage, right? So one step is easy. We need to say, okay, self.storage equal, the storage becomes once bigger plus value. There's a reason why I'm writing it this slightly. I'm not using a pen, but it's going a bit far to explain it. We could also use append. It would just produce a little bit worse code. Okay, that didn't help. Is my disk full? No, I don't know. Okay, we can deal. I'm going to end pretty soon anyway. So that's the first thing. We increase the storage, but now we need to change our structure, right? We need to change the structure that says hidden class equals self.hidden class add field name, name.nexttheme, right? We need to switch to a different layout that says, that is like the old layout, but it adds a field at the end. And so now we need to do def add field self name. And here we make a new hidden class. And that hidden class has the old layout. Self.layout.copy. But it also has a new entry. And the value of that entry is the length of the old layout. So if before we had 0 fields, then the position of the new field is 0. If before we had 5 fields, then the position of the new field is 5. Return res. Right. And now we make an empty hidden class that looks like this. And right. So that almost works, but we haven't really won anything now, because as I said, we want to share the hidden classes between all the instances that have the same layout. That means we need to cache the hidden classes. Here we always make a new hidden class, and that's bad because it means that different instances with the same layout will have different hidden classes. So now we need to basically memorize the creation of these hidden classes. So we say if name in self.next return self.nextName. That's the memorization. And otherwise we say we store the hidden class that we make in here to reuse it next time, right? So that's the basic structure, and there are a few additional hints that we're needing. First, we can say that these two functions are elidable; they're pure because the layout of the hidden class cannot change. If we want a different layout, we're changing the hidden class from the instance. And also, if you ask for the next if you ask for adding a field, you get the same hidden class the next time because of the memorization. Here you can see that elidable isn't exactly the same as pure, because this function isn't pure. It mutates the next, but it's observationally pure. I mean, you cannot observe from calling this method from the outside that it's not pure, because the next time you call it with the same arguments, you will get the same result anyway. Right, okay, that's the one thing we need to add, and the other thing we need to add is that whenever we're reading the hidden class, we're promoting it, which means that we speculate on the fact that the layout of a field is of an instance is likely always going to be the same. Right, and that should be enough. Yeah, this is probably a bit hard to take in. So the approach, let's start two things. Let's start this, and we can also start another compile. The approach we took here is basically we split the instance, and we used our knowledge about how the language is used. We know that in practice instances always have similar fields, and we wanna use that fact. We wanna use that knowledge about the language use in order to make better machine code. And we do that by introducing this hidden class object, which basically splits the instance in a fast changing part, which is the storage. The values of the instance fields can change quickly, and into a slow moving part, which is the hidden class, which basically encodes our knowledge of the fact that in practice we probably won't we won't go and mutate the instance. I mean, we won't add new and differently named instance fields all the time in practice. Okay, something is wrong. Cannot prove that the object is callable. Indeed, it's not callable. Empty is just an instance. It's a global constant. Let's do that. Thank you, static typing. You were very helpful, but of course I should have written tests, and then the whole problem wouldn't have occurred. Okay, stuff is happening. So yeah, we split it. We split the instance into a slow-moving part that's shared between all the instances that look the same, and into a fast-moving part. And doing that, we replaced the complicated, or we didn't really replace the complicated data structure dict. We just hid it. We hid it into this. We hid it into the slow-moving part of the object, and here the JIT will never look because the JIT will optimize away the calls to the elidable functions. And it will instead only see reading out of the storage array, and reading out of an array is much more efficient than reading out of a dictionary because it's a fixed position, so it compiles into a move with an offset, and that's not very expensive. It's still a bit expensive, but not that expensive. So there's still something wrong. Operation cannot succeed. Set item, right? Because what we want to do here is we want to add it to the layout, not to the self. More waiting. Oops. Right. Okay, we're waiting in parallel again. That's great. It's very efficient. It's a 2-core waiting. Here we're running the test that will give us the graph, and in the other tab we're producing a C binary to actually run some benchmarks. Oops. Okay. Let's see. Okay. There are no calls. That's great because calls means hash map lookups, and they're expensive. So that means we cannot have any hash map lookups. That's already pretty cool. So what do we have? So we have some instance here, and we read its hidden class, and then we have a guard value, which is the promote. That means we check that the hidden class is still the same hidden class that we had earlier. Then we read its actual class, and we have another promote. That means we check that the instance is still an instance of the class that we had earlier. Then we read the storage, and then from the storage we read the zeros position, right? Because in our test, where's our test? In our test, this instance only has one field, which is the incr field, and so the value is at the zeros position, right? So we read the zeros position, and then we have a guard non-null class here, and we check that it's a number. And then we read the num field out of the number, and then we have the usual stuff: an addition, a less than, a guard true. And now that we broke virtualizables, we have the annoying new here, but then the loop is quite efficient again. Right, addition, less than, and the annoying new down here. But yeah, the important part is really that we removed all the hash map access from instances, and instead we replace it by a guard of the hidden class to check that the structure didn't change, and if the structure didn't change, we can read from a fixed position out of the storage array of the instance. And yeah, so that's kind of the last feature that I do tonight. This has actually taken a lot longer than I was planning for, but it was fun, and my daughter hasn't woken up for her bottle of milk yet, so we're good anyway. So yeah, let's actually sort of summarize a little bit where we are while we wait for this one to do something. A number of features work quite well. Local variables work well. Global variables work kind of well with the cells, and method calls are inlined, functions are inlined. We have a polymorphic inline cache-like thing that's done by promoting the class. We have hidden classes to optimize the attribute reading out of instances and to specialize on the fact that in practice people aren't adding random fields all the time. And yeah, that's actually a pretty decent set of features for a little JIT. Yeah, it's actually quite comparable what PyPy is doing for the relevant features. PyPy still has a number of small improvements on what we implemented today. For example, for cells, we also type specialize the cells. So even if a global changes a lot, we will specialize the fact that it's always an int, for example. And then there's some more. I mean, basically, the hidden class implementation in PyPy is a lot more complicated because the object system of PyPy is a lot more complicated, but the basic approach is comparable. And yeah, the set of features is actually pretty reasonable. So what are the big things that are missing? I mean, I ripped out virtualizables because they were broken in some way that I didn't understand. That's probably fixable with a little bit of thinking or me asking the right people out of the RPython project. And then I think we're doing pretty well for the features that the language actually has. And then other features that we would need if we added language features, a very typical next thing that we would probably optimize is if the language had lists, then we should probably optimize the lists, because lists are also in dynamically typed languages are very general. Usually you can store all kinds of attributes into all kinds of objects into lists, but nobody does that in practice. In practice, the lists are type homogeneous, so we should have a more specialized implementation of lists that is optimized for storing just floats, for example. But we don't have lists, so we don't have that problem. Right. Let's wait a little bit longer. JIT compiler was generated. Now it's optimizing stuff. I want to make it run something. I mean, the first thing that we run was, I'll copy the binary away. That was the version where we only optimized locals and cells, I think. So the one that we get now really has everything. Right. Yeah. Actually, yeah. Let's while we wait, we can compute a speed up. Right. Let's compare this. Oops, in the wrong directory. Let's compare this. Right, 1.67 seconds, so we can add a 0 to the number of iterations. So just as a reminder, this is not translating anything. It's running as a Python program on top of PyPy, which makes it a bit faster, but not really super fast. And it's simply an empty loop with 10 million iterations. Right? Let's actually, just for the heck of it, let's write an empty loop with 10 million iterations in Python. And check how quick that is. Quick. Right. And once the we have one binary around. Let's level up. Looks like this. How quick is that? So quick. Right, we're faster than PyPy. That's amazing. So PyPy runs 10 million iterations of an empty loop in 0.16 seconds, and we do it in 0.103. There are complicated reasons for that. I mean, yeah, I don't actually know. It's a good question why PyPy is really slower here. We can look at the JIT statistics to maybe learn a little bit. Right. I thought that maybe the code generation itself takes a long time because the code generation is included in the timing here, right? But the code generation takes only 0.004 seconds, so that can't have been it. So it seems that the loop that we make for this interpreter is really a tiny bit better than what PyPy makes. Ah, no, wait. We have a slightly... For loops are slightly more complicated than while loops because they have an iterator. So we should do this to make it even closer. Doesn't seem to have changed much. Made it slightly worse. The other thing we can do is we should use floats here, which I don't suspect should make it faster, but you never know. Because in logs everything is floats. Ah, okay. It got slower because we started compiling C code, and the C code is using many cores. The compilation is using many cores, so it's simply that the machine is more busy. Benchmarking is hard. Okay, but it also means that we will get a new benchmark soon. Actually, while we bench inst.logs. Right. Let's copy. Oops. Let's copy this function here into a top-level file. That's the last thing we'll do, is run this instance-based benchmark. We need 10 million. Is it 10 million? Yeah. Right. Okay. So now we can compare the empty loop. Actually, we can be fancy and run it multiple times. It's so quick anyway. But those numbers are worthless because we're still competing with compilation and streaming for CPUs. So this should be taken with a grain of salt. But yeah, okay. So it takes that long. Right, and that's the version with without instances. And now we can do the instance version, and we should time it. And remember that this is the binary that was still doing very bad things around instances, so it's not fast. It's an easy 70 times slower. And that's still using the JIT, right? If we run that on top of PyPy, then it's lots faster still, probably. And now I removed a lot of zeros. I removed 1, 2, 3, 2 zeros. So in practice, it should be 100 times that. Right. Oh, this is all very unscientific. Right. Okay. So now we have the final binary, the binary that has much better instance handling. Right. And if we use, let's actually rename it to not lose it. Target to target C02 instance hidden classes. And if we run that, it should hopefully be faster. It's not, is it? Oh, it is faster, right? Okay, that's acceptable. So it's still a lot slower than, is it back to 1,000,000 here? Yeah, it's still a lot slower than just using a regular while loop without any indirections. Why is that? I don't remember what the difference was. We would have to look at the traces again. But we definitely made instance a lot faster by introducing from here to here. We definitely made instance a lot faster by using hidden classes, right? Yep, I think unless there are questions in the chat, that's it for tonight. Yeah, we made a JIT. We made. I would kind of bet that we made the fastest logs implementation in existence. If anybody knows another one that's JITted, I would love to compare it. Maybe I'll do that in another stream. But that's it for tonight, I think. Let's commit that. We didn't have to write a single. We didn't have to read any assembler. We only had to interact with this weird intermediate representation that we had to get used to. But how is that not a JIT? Of course it's a JIT. Do you want to look at the machine code? Rule says it's not a JIT. I don't actually have the C implementation around, but so I can't compare it against that, but I'm sure we're much faster because the C implementation is still an interpreter, and this is not an interpreter. It really makes machine code out of the logs program. And if you want to, no worries. I mean, I also need to say that this very meta approach that we're using, that is poking at an interpreter to tell a JIT generator to do different stuff and then produce machine code, is very head mangling, and it takes a while to get used to. So in addition, I might be not explaining it too well. Anyway, I want to convince you that it's a JIT, and I'm not sure I can come up with the right magic incantations, but we can dump the generated machine code, right? You can say, let's run this, and then We produce this out file that contains dumped machine code. We have another tool, which I never know how it works, but maybe I can find it. No, maybe not here. Here, no. Backend tool, view code. Lots of messing with Python path tonight. Right. So what this did is it told the binary, after you produce machine code for x86, please dump it to a file. And then we can use another viewer to look at it. Now my problem is that I'm a very strange kind of JIT person who does not actually know how to read machine code. So there's a lot of strange machine code, and most of it we don't really care about. But one of the things here is it's strange bootstrapping code, and it does weird stuff. But one of the things here is will contain the machine code for the loop that we have. And now if somebody from the chat can tell me what the x86 SSE instruction to add floating point numbers is, we might be able to find it. There's lots of stuff here. All of that is not really important. So we need to look at one of the loops. Is this a loop? Yes, but a weird loop. That's also, where's the real loop? Could the real loop please say hi? Actually, we can cheat. We can look at the not here. Here, I can find out what the name of the instruction is that the JIT will generate. JIT backend x86 assembler maybe, and then we have sorry, increasing the font. Let's look for float add, and it's add SD, I think. Right, it looks plausible. Wait. We're not finding it. Why not? I would have hoped that we find that in the output somewhere here. Can we find it in the textual output? Search. Yes, we can. So this is the thing that we need to find. Right. So let's also check what a floating point comparison looks like. Float less than. That's a compare op float, which is complicated. So this is the JIT backend that we compiled in. This maybe. ucom ISD. As I said, I really don't know any machine code. Which I agree is a strange property to have for somebody who's working on JITs. But I'm really more of a middle-end person. Why is this loop so complicated? I would be expecting a much simpler loop. Right. Yes, but it's hard to see the shape of it. But that's really our less than from where's the logs code? We're looking at the machine code that this weird machinery that we're using here generated from this logs code. And one thing it contains is it contains a comparison here. It's a less than this constant, and we can spot that. That's basically here. We have a whatever that instruction is, but it seems to be generated for floating point comparison, and we're comparing XMM0, which is an SSE register for floating point numbers, for doubles, and we're comparing that against R11, and R11 is, in the instruction before, we loaded a constant into R11, right? So, and that constant is probably 10 million, right? So we found the comparison. And I really don't know why the control flow is so complicated here. Why do we do this stuff? We go back up here. What do we do here? Complicated things. But one of the things we're doing is, wasn't there the add in there? What did I say the add was called? Add SD. Can we spot the add SD? It's here, right? So we go up here, then we end up in this block, and here we have the addition. Here, which is adding two SSE registers, which corresponds to this logs addition. And we should, maybe we can also see whether, right. I'm not quite sure I can understand. I'm not quite sure I understand where the one is loaded, right? The one here needs to come from somewhere too. So it's loading a constant, but it's doing it in a sort of indirect way by going via some offset somewhere, which I don't understand. So yeah, I mean, I'm not really sure. I would call it a JIT, because the end effect is that we're emitting machine code at runtime, which corresponds to logs code that we're running. So yeah, that, I mean, I call that a JIT. Are you happy with that, or not completely? Yes, but as I said, I try very hard to never have to read that code. The reason why it's that complicated, by the way, is that it's very branchy, because, I mean, in the previous view, we always ignored the guards, right? And the guards are complicated instructions. The guards will really leave the JIT machine code and go back to the interpreter. And I think all the side exits that you see here, all these things, they're really, I suspect that they're stubs for the guards, right? So they really say, oh, okay, I have a guard here, which is a compare and a jump L, for example. And then we go here, and that stub, it will load some code and then jump back to the interpreter. And there's very complicated machinery to be able to go back to the interpreter. Okay, Rule says he's happy. That's good. He's the original author of the interpreter that I butchered. Right. So yeah, so all these strange extra blocks that we see are really the guard stubs, and they make the machine code a lot harder to read than the trace. Not really. They really go to this very small stub of just a few instructions. It's basically this kind of. It's not really. I mean, it's a good question, because they're very. I mean, guards are very complicated. They're this very nice abstraction that we can ignore a lot of the time, but in reality, there's a lot of complicated. There's very complicated engineering effort and papers attached to how the guards actually work. Because when a guard fails, there are many levels to get right. We have a little stub of machine code, that's like 5 instructions, and that stub will jump to a generic guard handler. Yes, there are lots of them. Julian says there are lots of guards. And so the checking of the guards isn't a huge problem, right? The checking is most of the time, it's really just compare two things and jump if they're not equal. And that's not really expensive, because it's a perfectly predicted jump. They never, I mean, guards never fail in practice. I mean, 99% of all guard executions will never fail. So for the CPU, it's not very expensive to check them. It's just that when they do fail, it's very hard to do the right thing, because you really need to, you are somewhere deep in the generated machine code, and then you do very strange things to reconstruct the interpreter state as it would, like it would have been if we hadn't been using a JIT. So the whole reconstructing of just the right state of the interpreter, we need to fish the right AST, and we need to build we need to build all the objects that we didn't allocate, and it's really another very complicated corner of the JIT compiler. Yes, right. And yeah, indeed, different JITs do this very differently. I mean, guards, even non-tracing JITs have guards. It's in a more traditional method JITs, it would be called a de-optimization point, and there's a lot of literature around ways to do de-optimization efficiently. So yeah. So are there any other things that you want me to answer, or please write the most confusing part into the chat so that I can talk about it the next time or something. How's my disk space doing? Okay, still fine for a couple of more minutes. Right, yeah, so I should have prepared a little bit better and built the official logs C implementation so that we can compare performance against that. But my gut feeling would be that we would be doing pretty well, because it's garbage collected, it allocates a lot, and its garbage collector is probably not super tuned, and so I find it hard to believe that it would really beat that here. But I should have checked that, and maybe I will still do that in the next stream or tomorrow or something. Right, let me actually push that. Right. Okay, and I think, given that there are no more questions showing up, I think I'm going to end here. It's getting rather late here. This was took longer than I thought and was a bit more exhausting than I thought, but I had fun. If there are any follow-up questions, tweet at me or write me a mail or something. Yeah, and feel free to play around with this or whatever. Thanks everybody, and talk to you the next time. Bye.